All right, let's dive in. Today, we're talking about a massive shift that is completely changing the game for AI engineers. For a while there, most of us were building apps on top of APIs from places like OpenAI. But things are changing, and they're changing fast. Now, more and more of us are running these incredible open-weight models ourselves. And that means we gotta start looking under the hood. And that really brings us to the core question here, right? Why on earth do we, as AI developers who live and breathe software, suddenly need to start thinking like hardware engineers? Well, it's because the entire foundation of what we do is shifting right under our feet. Okay, so think of it like this. For years, you were the API user. Your world was pretty simple. You had the API on one side and your user's needs on the other. That was it. But now, many of us are becoming the model runner. We're firing up models like Llama 3 on our own machines. And when you do that, a whole new boss enters the room, the hardware itself. Suddenly, performance, efficiency, cost, that's all your problem now. And to solve it, you've got to understand the machine you're working with. All right, so how do we even start to think about this? Well, there's this brilliant analogy from the good old days of software development that just frames this whole challenge perfectly. It's called Use the Index, Luke. Look, you almost never have to build a database from the ground up, right? I mean, who does that? But pretty much every single developer has to use a database. And to use it well, to not write queries that take forever, you need to understand this thing called an index. It's this special structure that makes finding data super, super fast. You don't build it, but you'd better know it exists and how to make your code use it. And that just nails it, doesn't it? The goal here isn't to turn you into a GPU architect who designs silicon. No way. The goal is to give you just enough knowledge so you can use the tool effectively, so you can tap into the unbelievable power that's already sitting there, waiting for you. It's all about knowing which buttons to press. So to use a GPU the right way, we have to get its core philosophy. And it is completely different from a normal computer. It boils down to this one crucial idea. GPUs are all about high bandwidth, not low latency. And to really get why this matters, we gotta take a quick trip back in time. Remember the 90s? That was the era of the free lunch. Every year, computer chips got faster. Their clock speeds just kept doubling, and all of our software would magically run faster without us doing a thing. But then, around the early 2000s, that party came to a screeching halt. We basically hit a wall, a physical limit, and the entire industry had to find a new plan, doing more things at the same time. I love this quote. It's so blunt, but so true. The scaling of latency, of making a single task go faster, it died during the Bush administration. It's a relic of the past. It's not coming back. We have to think in parallel now. And this isn't just a hunch. There's actually a name for it, Patterson's Law. And what it says is that over time, bandwidth, how many things you can do at once, improves way, way faster than latency, how fast you can do one thing. We're talking orders of magnitude faster. For every 10x improvement we've eked out in latency, we've gotten a 100x improvement in bandwidth. The game is all about doing more all at once. And that is where GPUs are just in a league of their own. They take this idea of parallelism and turn it up to 11. You know, a really beefy server CPU can run maybe a couple hundred things at the same time, which is impressive. But a modern GPU, like an H100, it's running over 16,000 parallel threads. I mean, just think about that. On every single tick of its clock, 16,000 different calculations are all moving forward. It's just a staggering amount of parallel firepower.
Okay, so let's bring it all back. We had our database analogy, use the index, Luke. So what's the GPU version of that? What's the secret index inside this beast of a parallel machine that we need to learn how to talk to?
Well, here it is. If you take one single thing away from this entire explainer, let it be this. This is your new mantra. Write it down. It is, use the tensor cores, Luke. So what in the world are tensor cores? Think of them as hyper-specialized workers on the GPU assembly line. They are not generalists. They are designed from the silicon up to do one thing and one thing only, but to do it with absolutely face-melting speed, multiplying a big grid of numbers by another big grid of numbers, a matrix multiplication. That's it.
That is their one glorious purpose. And if you don't believe me, just look at the numbers. This is where it gets absolutely wild. On H100, the general purpose cores, the CUDA cores, they give you about 60 teraops of power. That's a ton. But the specialized tensor cores, they deliver 2,000 teraops. The vast, overwhelming, mind-boggling majority of a GPU's raw horsepower is locked away inside these things. If you're not using them, you're leaving almost all the performance on the table. It's like buying a Ferrari and never taking it out of first gear. Okay, so this is where the rubber meets the road. Knowing this isn't just some cool trivia fact. It fundamentally changes how you should approach building with AI, and it actually creates this surprising new advantage for smaller models. So how do we use the tensor cores? We have to feed the beast what it wants. And what it wants is a giant all-you-can-eat buffet of matrix math. The problem is, when we generate one token at a time from a model, that's a matrix vector operation. It's a tiny appetizer. To unlock the real power, you have to upgrade your task. You have to give it a big batch of work to do all at once. So think about it this way. The old, inefficient way is asking your model for one single answer. That's a matrix vector op. You're not even scratching the surface of what the GPU can do. But the new, hardware-aware way, you ask for 100 answers all at the same time. You stack them up. That turns the problem into the beautiful matrix operation that lights up those tensor cores. And the crazy part is, doing it this way can be almost as fast as generating that single answer. And this is where things get really interesting and kind of backwards from what you might expect. All of a sudden, it makes a ton of sense to use smaller, faster models. Why? Because you can run them in massive parallel batches, generate a whole slew of possible answers, and then just pick the best one. And this isn't just theory. People are doing this right now. You can take a smaller model like Llama 3.18b, and for a coding task, you generate 100 different solutions at once. Because you're batching that work and using the tensor cores, you can actually match the quality of a monster model like GPT-4o. You get the same quality, but way faster and way cheaper. That is a total game changer. All right, so let's tie this all together. This isn't just a technical detail we've been talking about. Understanding this principle literally gives you, the AI engineer, a brand new superpower. So let's just walk through the logic one more time, from start to finish. The free lunch is over. All the performance gains now come from bandwidth, from parallelism. GPUs are the absolute kings of bandwidth. But that power isn't spread out evenly. It's concentrated in these things called tensor cores. And what do tensor cores do? Just one thing: matrix math. So the key to everything is to feed them what they crave. Batched operations that look like matrix math. That's how you unlock their power. And so I'll leave you with this one big question. We've just figured out that if we use our hardware the right way, certain kinds of massive computations become almost free. So the question to you is, what does that unlock? If you can suddenly generate 100 or even 1,000 possible answers in the same time it used to take to get just one, what kind of crazy, brilliant, impossible things can you now create? The answer to that is now up to you.